All right. So the interesting, this damn camera straight. Interesting thing about these three sine waves is that uh, if you were to graph, let's say, this graph minus that graph. So when you have uh, sine of x minus 120 degrees, that's the phase shift. So this is B phase, right? You subtract that from A phase, sine of x. When you subtract these two, you're going phase to phase. That's the voltage drop. You're not going phase to ground, you're going phase to phase. So if you were to graph this, just to make the math simple, let's just say the amplitude right here is 1. All these, the B phase, the peak voltage up here of all these phases, A phase, B phase, C phase, let's say the peak is 1. Okay, instead of like 4,000 volts or whatever, 4 kV, instead of that, let's just make it simple. Let's just call it 1. The amplitude is 1, right? Well, if you were to graph the phase to phase voltage, like B phase minus A phase, for example, if you were to graph that, okay, I'm gonna graph it in orange. If you were to graph phase to phase, interesting enough, so like B phase would be down here, right? If it would continue, right? And then A phase goes like back up here, and so on and so forth. Where this graph meets, your phase-to-phase voltage is where it's at 0, because the difference here between the graph, the blue graph and the A graph, the difference is nothing, right? There is no difference because they meet. So the phase-to-phase graph, this is where it would be at 0 value. Another intersections right there would be at the 0 value, right? So that be at 0. So if you were to graph it, the phase-to-phase voltage, the difference between here and here is humongous, right? So it'd be up here, and then